I have started recording the class and I am now sharing the screen. Can you please validate if you are seeing the presentation page? You can write from the chat board. Can you see the page? All right. Thank you. Thank you. And now, so we are going to talk about the origin of the exponential random variable. So up to this point, I have explained that there is a random variable that is called exponential random variable, okay? And this exponential name, exponential, comes from the function e, okay? And it has a weird PDF. The probability density function has a weird shape. It has a constant half-life. So what do these mean? Actually, we need to explain. So there is an origin of the exponential random variable. So this random variable is not an ordinary random variable, okay? It is a magic behind it, okay? So remember the Poisson random variable from the video presentations. I have mentioned about the Poisson random variable. Again, it had a probability mass function because it was a discrete random variable, as you remember. It had a different probability mass function, a weird probability mass function. And there is a relationship, there is an important relationship between exponential random variable and the Poisson random variable, okay? So it says, consider a certain event such as arrival of customers to a supermarket, okay? Now, throughout the day, as the supermarket opens at, let's just say, 10 a.m. and it stays open until 10 p.m., okay? Throughout the day, from the entrance, people are arriving, okay? So let's just call these arrivals an event, okay? The arrival events, okay? Every time a customer arrives, we are called that in events, okay? Suppose the number of arrivals that occur in an hour follows Poisson distribution with rate parameter lambda. Okay, so we say that in an hour, okay, in an hour, the number of customers arriving in the supermarket is going to be a random variable because we cannot simply determine the arrival times of these customers. Okay, they are not coming with respect to the appointments that they have made, okay? So this is not a patient's room in a hospital, okay? There are no appointments. Therefore, in the following 1 hour, how many customers are going to arrive is going to be a random variable. It is going to be an unknown value. However, let's just say it is modeled by a Poisson random variable with rate parameter lambda, which means if you remember from Poisson random variable, the expected value of a Poisson random variable is also equal to lambda, okay? The rate parameter of a Poisson random variable is also equal to its expectation. And the expected value of a Poisson random variable is equal to lambda, okay? So we say that on the average, lambda arrivals are going to occur per hour, okay? In that case, we can also model the time between two consecutive arrivals. So consecutive means what? Okay, one arrival, then happens another arrival. Okay, these two arrivals are consecutive to each other. Okay, if there are no other arrivals between these two, there is no other arrival between these two, we say that these two arrivals are consecutive to each other. Okay. And the time between two consecutive arrivals is exponentially distributed, again with rate parameter lambda. So you see, Poisson random variable models the number of events occurring per time unit, whereas the exponential random variable models the time between two consecutive events, okay? And if we say that in a certain time unit, the number of events occurring is Poissonly distributed, then the time between two consecutive events, for these events, the time between two consecutive events is going to be exponentially distributed, okay? So the relationship with Poisson and exponential random variable are like this. So Poisson random variable, exponential random variable. So these are like twin siblings, okay? Twin siblings. However, one is a brother and the other is a sister, okay? So the difference goes like this. So these are twin siblings. However, one is a discrete random variable, the other is a continuous random variable. One models the frequency of events, Poisson models the frequency of events, whereas exponential random variable models the period or duration between the consecutive events, okay? So the average time between two consecutive arrivals is 1 over lambda hours. As an example, if I tell you on the average 10 arrivals occur to the supermarket, okay, per hour. So in any hour, the average number of arrivals is 10. Okay, we say that 10 customers per hour. This is the arrival rate. 10 is the lambda. Okay, 10 customers per hour is lambda. In that case, the average duration between two consecutive arrivals is going to be 1 over 10 hours. 1 over 10 hours, which is basically going to be 6 minutes. The average time between two consecutive arrivals is going to be 6 minutes, which is 1 over 10 hours. Okay, this is the reason why the exponential random variable's expectation is equal to the multiplicative inverse of its rate parameter, the reciprocal of the rate parameter. Okay, the Poisson random variable models the frequency of events, whereas the exponential random variable models the period of these events. The period means the time between consecutive events. So this is how exponential random variable is originated. It is originated from Poisson random variable actually, and the Poisson random variable is originated as a limiting case of the binomial random variable. You should have learned about this if you have watched the video presentations actually. Okay. So this exponential random variable is not a made-up random variable, okay? There is a relationship with it. If we model the number of events occurring per time unit as a Poisson random variable, then the time between two consecutive of these events is going to be modeled with an exponential random variable. So let's solve another question. This question is going to provide us information about Poisson distribution now. In a certain district, the number of traffic accidents occurring in any month follows Poisson distribution with a mean of 4 accidents per month, it says. Okay, with 4 accidents per month. Okay. Can you see the presentation, my friends? Can you see the presentation? Can you please respond to me? All right. Okay, if you can see, there's no problem. If anybody can see, then there is no problem. If everybody can't see, then there is a problem. Okay, so we say that the number of traffic accidents occurring in any month follows Poisson distribution with a mean of 4 accidents per month. Okay, we say that the average number of accidents occurring in this district is 4 accidents per month. This is the rate parameter of this distribution, lambda, 4 accidents per month. Okay, rate parameter is like speed unit. Okay, it has a unit of speed. Okay, number of events occurring per time unit. Okay, rate parameter. And it conforms the average value of this Poisson random variable. So lambda is equal to 4 accidents per month, and it is also the average value of the Poisson random variable. And in this question, we have a monthly time unit. Okay, monthly time unit. So we need to be consistent about this. Remember, we have a monthly time unit. So it says, what is the expected time between two consecutive accidents? The time between two consecutive accidents is actually exponential. Okay, so if the events are occurring according to Poisson distribution, then the time between two consecutive accidents is going to be modeled with an exponential random variable, and its expectation is going to be equal to 1 over lambda, which is 1 over 4 months. Okay, if we have a monthly time unit for 4 here, 4 accidents per month, then the time between 2 consecutive accidents is going to be 1/4 month per accident. Okay, 1/4 month per accident, which is 1 week. Okay, which is 1 week if you convert it to weekly units, the expected time between 2 consecutive accidents. What is the variance of the time between 2 consecutive accidents? You know, the variance of an exponential random variable is computed as 1/lambda square. Okay, so we are going to use this formulation as the solution of this question. So let's go to the next slide to see that. But before that, let's read part C. What is the probability that time between 2 consecutive accidents to be more than 6 weeks? What is the probability that the time between 2 consecutive accidents to be more than 6 weeks? Okay, so we are going to again use the exponential random variable, and we are going to look for the probability of this exponential random variable to be more than 6 weeks. Be careful now. The question gives us the rate parameter of the Poisson random variable, or the rate parameter of the exponential random variable, in monthly units. However, in this question, the question is asking something in weekly units. Okay, you need to be careful in converting this 6 weeks. How many months does 6 weeks represent? It basically represents 1.5 months. Okay, 6 weeks represent 1.5 months, we say. Now, in this question, as you can see, the definition in the question is given by a Poisson random variable, but every question here are about an exponential random variable. Be careful. So when you read the Poisson term in the question, this does not necessarily mean the questions are going to be solved with Poisson probability mass function or Poisson cumulative distribution function. As you can see, it is just the definition. We know that these events, these accidents occur according to a Poisson distribution. However, the question is all about asking the probabilities defined on the time between 2 consecutive accidents. So because of that reason, this question is actually an exponential random variable question, not the Poisson question. So Poisson is just giving us the key, the basic information that this question is related with exponential random variable. So we say that the time between Poisson events, the time between these accidents, we can call them Poisson events because they are occurring according to Poisson distribution. The time between 2 consecutive events are exponentially distributed with rate parameter equal to 4 accidents per month. Okay, and the expected value of the time between 2 consecutive accidents is 1/lambda, that is 1/4, that is 0.25 months, which is 1 week actually, and the variance of it. Remember, we should strict to monthly time units. Okay, there should be a consistent time unit. Therefore, the variance of the time in monthly units is going to be 1/lambda square, which is 0.0625. Okay, and the time unit here is month square. Okay, the variance, the unit of the variance is always square of the expectation. Okay, month square. But usually we do not write it because it does not form a physical meaning. Okay, the time unit here does not form a physical meaning. Month square does not form a physical meaning. Therefore, we simply say it is 0.0625. Now, in the last part of the question was asking what is the probability that the time between 2 consecutive accidents to be greater than 6 weeks. 6 weeks is equal to 1.5 months. Therefore, the question is asking us the probability of the random variable defined here to be greater than 1.5. Okay, which is 1 minus the CDF at 1.5. Remember, this probability can be computed by subtracting the probability of x being less than or equal to 1.5 from 1. And that less than or equal to probability is called the cumulative distribution function, or the CDF. And we basically write the CDF function, lambda is equal to 4, and the input is 1.5. This is going to give us e to the power minus 6, and it is going to be equal to 0.0025 approximately. Okay. Did you understand the relationship between the exponential random variable and the Poisson random variable, my friends? So you can answer from the chat board. Did you understand the relationship between exponential and Poisson random variables? Okay. Now let's practice it a little further. Okay, let's solve another question and practice it a little further. Okay. The mean time between successive telephone calls arriving randomly at a switchboard is 2 minutes. Okay, so the average time, so the switchboard is taking many telephone calls. Okay, and the arrival of these telephone calls to the switchboard occurs according to a. Actually, at this point, the question does not provide any information, so we need to read the remaining part of the question. So let me explain again. The average time between successive telephone calls or consecutive telephone calls is 2 minutes. Okay, all we know is this. The average time between the successive or consecutive telephone calls is 2 minutes. We know that the time between successive telephone calls are distributed exponentially. And what is the probability that the time between successive telephone calls will be between 90 and 150 seconds? So we know that the average time between these telephone calls is 2 minutes. This is the average value. And we know that the time between successive telephone calls is exponentially distributed. So this means what? Not every time the time between successive telephone calls is 2 minutes, okay? So the question is not telling us at every 2 minutes a telephone call is arriving. It is stating on the average at every 2 minutes. On the average at every 2 minutes, one telephone call is arriving. So sometimes we wait for 10 minutes for another telephone call to arrive from the previous one. Sometimes it takes only 15 seconds, okay? It follows an exponential distribution. And exponential distribution is a continuous distribution, remember. What is the probability that the time between successive telephone calls will be between 90 and 150 seconds, let's say? Okay. Now you see we were working in minute the time units here, but the question is asking the probability of an event, which is defined with seconds. So do not forget to convert these seconds into minutes. So how many minutes does 90 seconds make? It makes 1.5 minutes. And how many minutes does 150 seconds make? Okay, it basically represents 2.5 minutes. Okay, this is 1.5 minutes, this is 2.5 minutes. Okay, so we need to convert this. Now, the average time between the successive telephone calls is 2 minutes. So if we say that X here, the capital X, the random variable X, represents the time between the successive telephone calls, the question states that it is exponentially distributed. The question also states that its average is 2 minutes. Therefore, we need to extract this information by ourselves. The rate parameter of this event is 1/2 calls per minute, which means on the average, at every minute, 0.5 calls arrive. This is the frequency of these events. This is the period of these events. Okay, the period of these events, this is the frequency of these events. Okay, the average frequency and average period. Let me correct the term, average frequency, and this is the average period. Now we have defined that the time between the successive telephone calls is an exponential random variable where lambda is equal to 0.5. The rate parameter is equal to 0.5. The question is asking us this probability. What is the probability of the time between the successive telephone calls to be between 1.5 minutes and 2.5 minutes? And we can either integrate the probability density function, which is lambda times e to the power minus lambda x, where lambda is equal to 1/2, between the boundaries of these events, 1.5 and 2.5, and the integral will give you an approximate probability of 0.1859. Or you can directly use the CDF to calculate the same probability by subtracting the probability of x being less than or equal to 1.5 from the probability of x being less than or equal to 2.5, or basically subtracting the CDF value at the lower bound from the CDF value at the upper bound. Okay, and the CDF functions are 1 minus e to the power minus lambda x, and lambda is equal to 1 over 2. We basically plug in the x values and compute the CDF at these 2 points, and the difference between these two CDFs is also going to be equal to 0.1859. Okay, any questions about here? Do you have any questions? Did you understand the solution? Or let me ask it like this: did you understand the solution of these questions? So if I get a response, then I can continue. Okay, did you understand? All right, thank you. All right, now we are going to talk about another property of the exponential random variable. And this is a very, very important property, and most of the people who takes a probability course does not learn this thing. Okay, they do not learn this thing, unfortunately. Exponential random variables memoryless property. Okay, so please remember this name, memoryless. Okay, memoryless property. What does that mean, memoryless property? Now we say a random variable x is said to be without memory. We say that the random variable x does not have a memory, or we say x is memoryless if it satisfies this condition. Okay, so this means what? The probability of x being greater than s plus t, given that x is already greater than t, if this probability is exactly equal to probability of x being greater than s for any s and t assignment, okay, it doesn't matter s and t, what s and t values we choose, okay, it doesn't matter as long as they are non-negative. If the random variable satisfies this equation at all times, then we say that it is memoryless. Now you may say that, I mean, how this equation have a physical meaning. Okay, what is the physical meaning of this equation? So let's try to understand what this equation states. Okay, suppose now x denotes the lifetime of an instrument. So let's just say it is the lifetime of a digital device like a television. Okay, it is the working lifetime of a television or washing machine. Okay, or another digital device like a computer. Okay, and we say that x is memoryless. Okay, if x is memoryless, if the lifetime has no memory, okay, in that case, it needs to satisfy this equation. What does that mean? So let's just say we have purchased a computer, and for t years, we have this computer properly working. So we have observed that its lifetime exceeded t years. Okay, up to this point, it has worked for t years. This is observed. And we are looking for this probability, its total lifetime to be greater than s plus t, which means it has already worked for t years. What is the probability that it also works for an additional s years? Additional s years, be careful. And this probability is equal to the probability of a newly purchased computer to have a lifetime that is greater than s. Okay, so for a computer that has already worked for t years, the probability of additional working for an s years, if this is equal to the probability of a newly purchased, okay, the brand new, okay, the first-hand computer to work for s years, if this equation holds, then we say that this device has no memory, or the lifetime of this device has no memory, which means it doesn't wear down. Okay, it does not remember for how much it has worked. Okay, it doesn't get tired. Okay, at some point it is going to break down. However, if it is working right now, it does not, it satisfies the conditions, of being a brand new device. Okay, it doesn't wear out. Now you may say that how this works. Okay, if you, for example, think about human life is not memoryless. I mean, if somebody lives for 70 years, then we know that the remaining lifetime of this person is not very much. Okay, so the probability of a person who lived for 70 years to live for an additional 10 years obviously is a lot less than the probability of a newborn baby to live for 10 years. Okay, so human life is not memoryless. However, the lifetime of digital products like computers, like printers, like light bulbs, like radio, digital radio, like television, okay, the lifetime of such devices may satisfy this memoryless property, or they may have no memory. Okay, in fact, there's a light bulb in New York right now. Okay, it is attached to a fire station, and this light bulb is properly working for more than a century. Okay, so whenever it is started to be used by the end of the 19th century, actually. Okay, and up to this point, up to this year, it is still properly working. They have not turned it off. Okay, the first time that the light bulbs were being produced, okay, in this manufacturing industry, they were produced with a very high quality, and because of that reason, they were not wearing down. So in today's technology, actually, we can do better and manufacture zero defect light bulbs, but they are not manufacturing it, because if they manufacture, then we wouldn't purchase new light bulbs. Okay, and this means they are consuming their own market. Okay, they are consuming their own market. Because of that reason, they try to manufacture light bulbs or digital devices which has a certain lifetime, average lifetime, and which does not follow exponential distribution. So at some point, the device performs suicide to itself, actually. Okay, so these things happen to be happening. These things are happening for example, printers. So after the term for the guarantee period, okay, sometimes the printers, they break down, and the reason for that is because that they may have a suicide chip within them. Okay, otherwise, digital devices, they have a very high quality. They can basically work for a long lifetime, which can be modeled with an exponential random variable. Okay, so we say that if the instrument does not remember that it has already been in use for a time t, and the remaining lifetime of this device has the same probabilistic properties as the lifetime of a newly purchased device, then we say that this device has a memoryless lifetime. Okay, it doesn't remember for how many years or how many days or for how long that it has survived. The remaining lifetime of this device is going to have the same probabilistic properties of the same device, a newly purchased device. In that case, we say that the lifetime is memoryless. Now, here's the thing. Exponential random variable is memoryless, and it is the only continuous random variable that follows the memoryless property. Okay, so let's explain the memoryless property in this equation again. We said that if an item, if a device works for t years, if the lifetime, if the random variable is greater than t, what is the probability of it being greater than an additional s amount? Okay, if this probability is equal to the probability of a lifetime of this device or the random variable to be greater than s, then we say that this random variable has the memoryless property. Now, this is a conditional probability statement, and this conditional probability statement can be expressed as the probability of the intersection of these two events divided by the probability of the given events. So probability of x being greater than s plus t intersection x being greater than t divided by probability of x being greater than t. And this intersection, if you look carefully, the intersection of these two events is what? The probability of x being greater than s plus t. Remember now, this event, x being greater than s plus t, is a subset of x being greater than t. And therefore, the intersection is this event, okay? So the ratio between the probability of x being greater than s plus t, because the intersection is reduced to this event, between the ratio between the probability of this event and the probability of x being greater than t is equal to probability of x being greater than s. Or in other words, if this intersection's probability is equal to the product of x being greater than t and x being greater than s, if this probability is equal to the product of these probabilities, then we say that the random variable is memoryless. And this only happens for exponential random variable in the continuous universe, okay? Among all continuous random variables, the only random variable that satisfies this property is the exponential random variable. Now check this out. Exponential random variable has memoryless property. So let's prove that. Let's see that it has the memoryless property. Remember now, for a random variable to have a memoryless property, this conditional probability of an additional lifetime of s, given that it already has survived for t years, should be equal to the probability of a newly purchased device's lifetime to be greater than s. Okay, and we are going to show that this is true for exponential random variable. So we have said that this conditional probability can be expressed as the ratio between the probability of the intersection of these two events and the probability of the conditioned event. And the intersection event is x being greater than s plus t. And this is equal to 1 minus CDF, the cumulative distribution function at s plus t. Remember, this tail probability is computed by its CDF from the complement event. And here, the probability of x being greater than t is also 1 minus probability of x being less than or equal to t, which is 1 minus CDF at t. And if you plug in the CDF functions, remember the CDF function is 1 minus e to the power minus lambda t here. You are going to get e to the power minus lambda t in the denominator, and in the numerator, you get e to the power minus lambda s plus t. And the ratio between these two is e to the power minus lambda s. And this is equal to the tail function at s. Okay, so this is equal to 1 minus the CDF at s, remember. So this is going to be equal for any arbitrary s and t value as long as they are non-negative. Okay, you can also prove that the exponential random variable is memoryless by showing that this probability expression is equal to the multiplication of these two probability expressions. And this probability expression is e to the power minus lambda s plus t. And these probability expressions are respectively e to the power minus lambda s, e to the power minus lambda t, and e to the power minus lambda s. I'm sorry that they are given in different orders. So this probability expression is equal to e to the power minus lambda t, and this second one is equal to the first one. Okay, they are given in different order. So you see, exponential random variable is memoryless. Okay. However, I mean, even though you are being convinced that it is memoryless, unless you solve a question about an exponential random variable, you still do not understand this magical thing. So exponential random variable is memoryless. We need to support this fact by solving a question about it. Now, there is another question here. I have told you that exponential random variable is the only random variable that is continuous and that is memoryless. Okay, it is the only continuous random variable that is memoryless. I am asking you this question. What is the discrete counterpart of the exponential random variable? So tell me a random variable that is discrete and that is memoryless. There is also another random variable that follows the memoryless property, and it is going to be discrete this time. Which random variable satisfies this property? I am asking you this question, and please answer this after thinking. Okay, so I'm giving you this 20 seconds to think about this. Please answer which random variable is memoryless and it is also discrete. So do not answer fast. Is there anybody who follows me at the moment? Are you there? You are there, but you do not have the answer, I guess. Dennis, I'm sorry. Not Poisson. Poisson is the fast one, because so you understood that exponential random variable and Poisson random variable, they are like twin siblings. However, Poisson random variable, it's not memoryless. So let me tell you this. You are tossing a die and you are going to stop. You are going to stop until you get a 6. Okay? Yeah, you are going to continue tossing until you get a 6. You are going to stop when you get a 6 as a result of this procedure. Okay? Now I am asking you this. You have tossed the die for 20 times, but you still did not get a 6. Did not get a 6. What is the expected remaining lifetime or expected number of tosses? Expected number of tosses that you are going to perform until you get a 6. Okay? Exactly. Geometric random variable. Okay? Remember now, the expected number of die tosses until you get a 6 is 6, right? Because the success probability is 1/6, and the number of trials that you need to perform is, on the average, 6 trials until you get a 6. Okay? Now, if you perform this experiment and you still do not get a 6 for 20 tosses, okay, for 20 tosses, you didn't get a 6 at this point. What is the remaining average number of tosses that you are going to perform is still 6, because the remaining tosses probabilistic behavior is independent of the previous tosses. Okay? I mean, if somebody cannot toss or cannot get a 6 after 1 million tosses, it doesn't matter. For the remaining tosses, this probability is still 1/6. Okay? So people usually make this conceptual mistake. I mean, if they cannot throw a 6 until in 20 or 30 tosses, okay, they say that, I mean, the next time I should definitely get a 6 now because I have a luck for that. Okay, the luck, the chance that you are going to get a 6 does not increase or decrease. It is always 1/6. And because of that reason, geometric random variable is what? Geometric random variable is the only memoryless discrete random variable. So we have two random variables which follow memoryless property. The continuous memoryless random variable is exponential random variable, and the discrete memoryless random variable is geometric random variable. Okay, and if you check the probability mass function of the geometric random variable, again, it looks like very similar to what? It is going to be very similar to the PDF of exponential random variable. It is, if you check that, it is going to look like a discretized version of the exponential PDF. Okay, so this is just an additional information. The memoryless property of geometric random variable actually is not very important for us, as it is important to know the memoryless condition of exponential random variable. Okay, now let's solve a question about this. The lifetime of a radio is exponentially distributed with a mean of 2.5 years, it says. If Dwight buys a brand new radio, what is the probability that it will be working at least for 10 years? Okay, so we have an exponentially distributed lifetime for this radio, and its mean is 2.5 years. So if x denotes the lifetime of the radio, then the expected value is going to be 2.5 years, which is going to be equal to 1 over lambda. Hence, the rate parameter lambda is going to be 0.4 radios per year. Okay, so on the average, 0.4 radios break down in every year on the average. Okay, the rate parameter is the inverse of the expectation for exponential distribution. Now coming to the questions. If device buys a brand new radio, what is the probability that it will be working at this for 10 years? So Dwight purchases a new radio, which has a lifetime of X. What is the probability that it works more than 10 years is the probability of X being greater than 10, which can be computed by subtracting the cumulative distribution function at 10 from 1. And it is going to be equal to e to the power minus 4, where if you choose lambda to be equal to 0.4 and the input of the CDF is 10, the probability is going to be 0.0183. Now, if we go back and read the second question tells us this. If Dwight buys a 5-year-old radio, what is the probability that it will be working after an additional 10 years? Okay, so Dwight purchases a second-hand, a used radio that is being used for 5 years. Okay, now we are interested in finding the probability of it working for an additional 10 years. Okay, so the question is expressed like this. We have observed that this is not a new radio. It has been worked for 5 years. It has worked for 5 years. We are looking for the probability that it is going to work for an additional 10 years, which means the total lifetime is going to be greater than 15. Or in other words, the probability of this radio to be having a lifetime that is greater than 15 years, given that it has already worked for 5 years. Now, this conditional probability can be expressed in this form by taking the ratio of the probability of the intersection of these two events and the probability of the conditioned event. And the intersection of x being greater than 15 and x being greater than 5 is basically x being greater than 15. Hence, the probability in the numerator is 1 minus CDF at 15, and the probability in the denominator is 1 minus CDF at 5. And if you plug in these values, you are going to get e to the power minus 6 over e to the power minus 2. And it is going to be again e to the power minus 4, which is again approximately 0.0183. Okay, so practically, we have solved this question by expressing this conditional probability, and we have not used the fact that exponential random variable is memoryless. Okay, we have basically practically solved the question with our previous knowledge. However, you can answer such a question by stating that exponential random variable is memoryless, and the additional lifetime of a reused radio has same probabilistic properties as the lifetime of a brand new radio, or the radio does not wear out. Okay, it doesn't get tired. So the answer is going to be the same as in part A. So without writing these equations, without solving this question numerically, you can simply state that according to a memoryless random variable's properties, the lifetime, the additional lifetime, will have the same probabilistic properties as the lifetime of a brand new device. And we will say that the additional lifetime's probability to exceed 10 years is going to be the same probability as in the first part. Okay, so did you understand this simple question? Okay, did you understand the memoryless property? Yes or no? All right. Okay. Obviously, if you do not understand these things, you can actually learn about them during the recitation videos, and you can also rewatch these videos again and again. So let me solve another question. Let me check. Yes, this is the last question about exponential random variable. Then I'm going to give you a break. Okay. If the life of a component has an exponential distribution with a mean of 100 hours, what is the probability that it will last 400 hours given that it has already survived for 200 hours? Okay, first of all, the life of this component is exponentially distributed. It is an exponential random. It can be modeled with an exponential random variable. And I am asking you this question: what is the rate parameter lambda? What is lambda here? In this question, can you tell me what the lambda value is, rate parameter is? Somebody? Okay, in the following year, maybe. Can you give me the answer, the lambda, the rate parameter of this exponential random variable in the slide? So it has a mean of 100 hours. The expected value is 100 hours. If the expected value is 100 hours, what is the rate parameter lambda? Thank you, Beyza. It is 0.01, obviously. If the expected value of this random variable, if the life of this component is 100 hours, then the rate parameter lambda is going to be 0.01 component per hour. So on the average, 0.01 component breaks down in every hour, okay? So this is the rate parameter. So you need to be careful about this. The probability of interest is this. We are asking this, what is the probability that it will last 400 hours given that it has already survived for 200 hours? The question is asking this, what is the probability that it is going to last 400 hours or the lifetime is going to exceed 400 hours given that X is greater than 200 hours. X has already survived for 200 hours. Now this probability is the same probability as the newly purchased component to exceed the lifetime of 200 hours. Okay, so we can say that since exponential random variable has no memory, so the additional 200 hours of lifetime has the same probabilistic properties as the newly purchased components working for 200 hours. Therefore, we can simply calculate this conditional probability by calculating the probability of a newly purchased component to exceed the 200 hours lifetime, which is 1 minus the CDF, and the CDF is 1 minus e to the power minus lambda x. Lambda is equal to 0.01, and the input is 200. Hence, the answer is e to the power minus 2, which is 0.1353. Any questions, my friends, here about exponential random variable? So that is all that I'm going to teach you about the exponential random variable. And next, we are going to deal with something much more important. So I am just going to stop the presentation recording at this point, okay? And